So there are many formalism for semantic parsing, such as your lambda calculus, and many of the lectures that I've given until now. So I introduce AMR, abstract meaning representation, as another formalism. But the reason that I like this one, it has a very good, it is a good trade-off between syntactic world of Noam Chomsky and semantic world of cognitive linguists. So if we combine the semantic world with syntactic worlds, we have a good meaning representation. So my research is at the intersection of these because I'm interested in common sense reasoning. It's the future of AI. I'm interested in graph neural networks as well as factor graphs and graphical models. I also like knowledge bases because, for example, at this intersection, we have some knowledge bases such as ConceptNet and Atomic, which are more sparse and more complex than what you have already seen in knowledge bases such as Freebase, which is very easy and very small in comparison to ConceptNet and Atomic. So my research is is in the intersection because I believe that it is more close to what human perceives and understands and do reasoning. So AMR parsing, we can see it as just sequence to graph transduction. But what kind of transduction I'm talking about? It's just a simple sequence to sequence model to obtain what concepts you need, and after that you just use the by-affine attention model of Professor Christopher Manning in Stanford, which is really beautiful for many problems. So the idea is we propose an attention-based model that treats AMR parsing as sequence to graph transduction. Unlike most AMR parsers that rely on pre-trained aligners, you should do aligner. You should align the sentence with the corresponding concepts. For example, you have done it in part of speech tagging, you have done it with semantic tagging, name entity recognition tagging. Many of those things are one-to-one correspondence. But the problem of AMR is that sometimes one thing is repeated several times. So it's not that much easy, and the alignment is not one-to-one. It has complex nature. Also, your AMR is not a tree. It is directed acyclic graph, dagger, or even a general graph. So it's much more complex than what you have seen so far. So this formalism, implementation of that, in order to get good F1 accuracy, F1 score, and good accuracy, you need to know something. So we interpret it as a sequence-to-sequence model to obtain these concepts, and after that, use the deep by-affine attention of Professor Christopher Manning to find these relations. So there are challenges in AMR parsing. Its property of reentrancy, because one word could be used several times. The same concepts participate in multiple relations. It has the lack of goal alignment between nodes in the graph and words in the text, and relatively limited amounts of labeled data. For example, I'm working on Persian AMR. We have very little data. I'm sure in many languages there are very little. For example, in Dutch language or in German language, there are very little labeled data, so people have struggled with these expensive data sets. So this is the task formalization, because we transform it into just a sequence modeling. But after we obtained the sequence, we should see the relation between them, and that is another task. So after we get these scores, we just use the basic idea that we use in semantic parsing or even in syntactic parsing, that we get the maximum of these, the total sum of our scores, and we know how to do it by just using maximum spanning tree. It automatically finds the best graph. So the architecture is like this. You can look at it as a sequence to sequence model. They use pointer generator. It's like, I've explained this in my playlist for summarization. It's an article from Professor Christopher Manning. It's an alternative to that Chinese article CopyNet. So both of these articles are interesting. Both of these models capture the fact that some of your words could be seen in the output. So we just copy them. And the rest of the world, such as possible, for example, is new, so it should be generated. So it's a combination of generation and copying mechanism. So there are two models, as I said, pointer generator to find the nodes, to find the concepts, and then deep biaffine classifier, it finds the relations between two concepts. So this is the extended pointer generator networks that I've explained in playlist for summarization. And finally, for edge prediction, we just use the deep biaffine attention of Professor Christopher Manning in his beautiful article of dependency parsing, I think. And I've explained this article as well. So this is a good structure that you will see in many articles because it's very natural. This is the simplest equation that you can make to relate some nodes. And you can create the scores and finally get what is the probability of head, and also for the label you can use the same analogy. And for the training, you should know that not only you need to know the labels, but also you need to know the head and the probability. You should maximize these probabilities or minimize the likelihood. And the prediction, for the prediction, we can, for node prediction based on final probability distribution, we implement both greedy search and beam search. And it has, of course, a pre and post processing that is explained in this figure.